In this video, we're going to have a look at something called the call stack. Now, we'll study stacks in quite a lot more detail later on in the course, but for now, think of the stack as a type of data structure where we can store all our functions. So in general, think about if you had a stack of pancakes. You start off with your plate, and your plate just sits at the bottom on the table like that, and when you cook your first pancake, you always add that one to the top of the plate. From there, when you cook a second pancake, you don't try and fit it in underneath or anywhere. You simply put the new pancake on top of the last one. And every time you cook a new pancake, you place that pancake on top of the stack. So you now have a stack of pancakes with the most recent one on top. So the recent pancakes on top, or the recent functions on top, and the first function or the oldest function at the bottom. And that's the basic idea of a stack, and as I say, we'll cover that in quite a lot more detail later on in the course. So the idea of a call stack is exactly that we start off with some base, and that comes from the operating system, and then from there, every time we call a function, we get a new frame. So it's called a frame that goes onto the stack, and each frame represents a new function. So we would start off and we would have our main function, and then that might call a function called fun1, and then that might call a function fun2, and then fun2 might then finish, it might do its job, return some kind of value, and so fun2 then gets removed from the stack, and then we resume where we were in fun1. So if we'd stopped at line 5 in main, and then on line 10 in fun, that had then called fun2, and so fun2 continues like that, and then at the end fun2 finishes, and so fun2 gets popped off of the stack, and then the execution continues from line 10 in fun1, and so that would then go on to line 11 and continue to do all the work that it's supposed to do. So in this case, if fun1 then called a different function, it might call fun3 after that, fun3 might call fun2, and then as we go, each function gets pushed and popped from the stack as it gets called and as it returns. Alright, so you can now see that there are three example functions that I've written here. We have our main function, and we see on line 1, 2, 3, 4, 5, 6, and 7. And so within that main function, we see that we have two integers, a and b, and we give them each values, and then there are two functions that we call. Those two functions are fun1 and 2. So let's say that if we had our source code, we'd maybe say that was line 8, 9, 10, 11, and 12, and maybe line 13, 14, 15, 16, and 17. So now, if this were running in our computer, what would happen is we'd start off with our stack being empty like that, and at the very beginning, when our program first launches, the frame for our main function gets pushed onto the stack. And so we now have a frame for that, and within a frame, we get space to store all of the local automatic variables. So in this case, we see that there are two variables that we need to worry about, and so there's a and b, and those two variables need space to get stored, and in this case, they get stored in the stack. And so the compiler will make sure that when it creates our program, every time the main function gets called, it creates space for a and b on that call stack within that frame. And so as the function moves into line 2, we see line 2 runs, and it goes to a, and it puts in the value 4. Then it goes to line 3, and it goes to b, and it puts in the value 58. On line 4, we then see, okay, we're now calling another function. So now within this frame, the compiler now makes note that we're on line 4 of our program. So let's call that line 4, and it remembers that. It then creates a new frame, and in this case, it's calling function fun1. So we then jump to line 9. And so in fun1, we're now on line 9, and the compiler will make sure that it creates space for all the variables that are inside this function. And so in this function, we see that we have a variable called c, and we have a variable called a. You can see that in this case, the compiler treats the variable a from main and the variable a from fun1 as completely separate variables. So even though they have the same name, because they're in a different scope, the compiler treats them as different variables. And so we can see that there's one version in the stack frame for main, and there's another version in the stack frame for fun1. So now the compiler goes in and we're on line 9. It sets the value 12 to variable C. Following that, it will go to line 10, and so it updates that line number. We go to line 10 and we see that in A it now stores the number 43. Following that, it returns the value 12. So usually what we would do is, if we were saving that value into some variable in the previous function, then that value that gets returned, so in this case 12, it would get copied into one of the variables inside the main function. But in this case, we're ignoring the output, and so does the compiler. And so from here, the function is now finished, and that function frame gets popped off of the stack. And so that disappears from the stack. And now the compiler says, where were we? Oh yes, we were on line 4. We've now completed that line, and so now it moves on to line 5. And so it sees that there's a function called to fun2, and so in this case it now creates a new stack frame. It knows that it's for fun2, that's the function there, and it goes and says we're now on line 14 in there. And again, it's got to create space for all of the different variables inside that function. And so once again, we have a variable called A, and now we also have a variable called D. So on line 14, it goes in, it executes it, and it says set the variable A to be 2. So it saves the value 2 inside that local variable. We then go to line 15, and it says set variable D to be value 5, and so that value gets saved inside variable D. And then after that, we see that there's another function call. So now on line 16, it remembers where we were previously in that function. So we were on line 16, and now we're making a function call, and so the compiler then adds on a new frame onto the stack. So again, it always goes onto the top. That frame gets added to the stack, and that frame is now for fun1 that we're calling from line 16. So from there, we need to make sure that we have space for all our local variables, and so we have space for C, we have space for A, and we now go in, we're on line 9. On line 9, we set the value of C. So we save 12 inside that variable. We then go on to line 10, and so on line 10, we set the value of A to be 43, and then after that, we go return C. Again, if we were saving the value somewhere, that value would then get copied from there into some space in fun2, but in this case we're not. So now the function is finished, and so that frame gets popped off the stack and it disappears. So that top one disappears, and now we continue back where we were in fun2. And so the compiler looks and it says, okay, we were in line 16, so now we move on and we're now on line 17. And then it sees that that function has finished, and so in this case that function's now done, and this frame gets popped off the stack. So that frame disappears, and the compiler then resumes, and it continues where we were previously, and it says, oh, where were we? It sees that we were in line 5 when we were in main, and so that line is now completed, so it goes to the next one, it goes to line 6, and so now we move on to line 6. We do whatever that's supposed to do, and in this case it's the return function, and so now we return 0, and this final frame gets popped off the stack, and the operating system takes control again. So now we've seen how the compiler manages function calls using the call stack. It's important to note then that there are two different ways that we can allocate memory for variables. And we see that these variables can be allocated automatically when we don't use new and we just declare the integer or declare the variable as it is. Or when we do use the new keyword, then what that does is that tells the compiler to allocate it somewhere else. In this first case, when it's automatic, that gets allocated on the stack. And we call those automatic variables because they get allocated for us and they get freed for us. When we use the new keyword, those get allocated on something called the heap. And so we've seen the stack. The stack is just the stack of pancakes that we always add a new frame onto the top of the stack. The heap, on the other hand, is just some other memory, and it's exactly what it sounds like. It's like a heap of laundry sitting in the corner, and we just kind of throw things on it as we need it, and we don't really know where things will go. There's no real structure to it that we know about just yet, and it's up to the operating system to decide exactly where memory should come from. And so in this case, what will happen is there are actually three pieces of memory that we're looking at here. So in this example, we can see that we've got an integer called a, we've got a pointer called p, and we've got the actual memory for the integer that we've allocated. So we can see that there are 3 different pieces of memory that we would need to think about now. So what will happen is when the main function gets called, it will get a frame on the stack. It will then say, we see that there are 2 automatic variables inside the function. There are 2 local variables inside this function, and the one variable is going to be a, and the other variable is p. It's the pointer. Then, as we go in onto line 3, 4, 5, as we go into line 2 will then say, inside variable a, store the number 42. And so the compiler goes into that address, and it stores the value 42. It then moves on to the next line, and we see line 3. So it then sees that there's the new keyword. And so in this case, we've got our heap sitting somewhere to the side. So we've got the heap over here, and we've got the stack over here. So in this case, what we now do is the compiler goes to the operating system and it says, please give me enough memory to store 1 integer in this case. And so the operating system will look through the heap, it will look for a little bit of space, and will find some block. That block will then have an address. So let's say that address is 0x36. So now what will happen is that memory will be assigned to our program, and so we're now allowed to access that memory, and no one else on the computer is. So this is now our memory, and we can now, the operating system gives it to us, it gives us that address, and we now save the address inside that pointer. So inside the pointer we save the value 0x36, and that means that that pointer is now pointing to that block of memory elsewhere. On line 4 then, when we say dereference p, so follow the pointer and then set the value to 5, what that means is that it says look up the address stored in p, which is 0x36, then go to address 0x36 and save the value 5. And so we now see, we should now be happy with this idea that we've got 2 variables locally, a and p, 1 integer and 1 pointer, that are stored on the stack, and then we've got 1 integer that is stored on the heap. Okay, so in this example we see that we've got 2 functions, and the functions make use of both automatic variables that are local to the function and automatically managed on the stack, as well as dynamically allocated memory that's allocated on the heap using the new command. So we start off, and as the program starts, we go into our main function and we get a frame on the stack for our main function, and the compiler will create that frame, and it will make sure that we've got space for all of the local variables inside that function. So in this case we just have C, and so it's allocated space for that variable C. Immediately we see that in order to give C a value, we have to call fun1. So the compiler then creates a new frame on top of the stack, fun1. It remembers that we were on line 7 inside main, and now we're inside fun1. In that frame for fun1, we'll see that it'll create a variable a, and it will create another variable for the pointer p. Remember, it's not storing the value 12 inside here because 12 lives on the heap. So inside fun1, we now see, okay, cool, we go on to line 2. Line 2 says save the value 4 into variable a. And so we go into variable a and we set the value 4. On the next line, we go to line 3, and we see that it's now asking for memory from the heap. So that we go to the operating system and say, operating system, please give us enough space for 1 integer. And in this case, we're saying we're setting the value of that integer to be 12 at the same time. So it allocates space and it sets the value, and then the operating system will return some memory address. So the memory address might be, let's say, 15, and 0x15, that address will then be stored into the pointer. And we always think of that as there is some arrow going from the pointer to that address in memory on the heap, and that allows us to access that value later. We then say, okay, cool, next line. So we're now onto line 4, and we see that it's a return statement for a. So in this case, we know that the value of a should be returned, and it should be saved inside variable c. So now the compiler will go in, it will say, take that value 4, and it will copy it into variable c. So that gets copied like that. That function is now finished, and so that frame will get popped off the stack. So in that case, the frame for fun1 will disappear like this. Now there's a very important thing to note. the compiler will continue running our program now from line 8. So it looks over here and it sees we were on line 7, we now continue on line 8. But what's important is that we had a pointer to this memory on the heap earlier. It was stored inside P, but now P is gone because P automatically gets destroyed, or rather the pointer itself gets destroyed once that function finishes. All the variables locally inside the function, all the automatic variables inside the function get automatically destroyed because that frame from the stack gets popped off. And so in this case, we now have memory that's allocated to our program. We have this block at 0x15 that contains 12. We have this memory that's allocated to our program, but that we can no longer access. We don't have a pointer to it anymore. There's no way that we can get the value. There's no way that we can set the value. And more importantly, the operating system still thinks we're using it. And so the operating system is not going to take that value back. It's not going to take that memory back. And so now we've got this memory that's going to be floating around in the heap for the entire lifetime of our program, and the operating system won't touch it, and it won't let other programs touch it until our program finishes. This is definitely a bug because now we've allocated memory that we can no longer use, and this bug is called a memory leak. And it can be quite dangerous because if our program runs again and again and again, over a long period of time, we may accumulate a lot of memory. And so this is often what happens when you have a program that might run for 5 or 6 or 10 hours, for example. If you've ever had a browser and you leave your browser running and you come back a day later and the browser is suddenly using 4 gigs of RAM, it's usually because of one of these types of bugs, where we allocate memory and then the pointer to that memory disappears because the function returns and we have no way of freeing that memory. The correct thing to do would be before that pointer gets destroyed. So somewhere between line 3 and 4, we would need to explicitly tell the operating system that we no longer need that memory. And so in this case, we would say delete P. And what that does is that tells the compiler to give that memory back to the operating system. It doesn't delete the pointer itself. We know that that only happens when the function finishes, but it says go to the block that P is pointing to, so 0x15, and give that back to the operating system. The operating system then takes that back and it can now add it back to its pool of memory, and it gives it to other programs that are running, or if our system asks for memory again, we might be given that block again. So in order to make sure that we avoid memory leaks, we always need to make sure that a new command, so a command that allocates memory, is always paired with a delete command. So finally, the last thing I'd like to do is to show you what the call stack looks like in an actual program in a compiler. So I've opened Qt Creator. This is the same IDE that we had in the last video on debugging. So I'm now going to create a new project. I'm going to create a plain C++ application just to illustrate things, and let's call this the call stack project. I then just accept all the other default commands, and now let's create some functions that were similar to the last ones. So we can create a function int fun1, and inside that function we'll have a, which has a value 4, and we'll have b that has a value 16, and let's have a pointer p that's going to point to some new integer with the value 12. And then let's just do something interesting. Let's just print out a followed by b followed by p dereferenced. Note that I haven't put spaces between any of these variables. We can then also say return b, and so that will now return that one. We can create variables on this side, and so we can create a variable called a, and let's give that variable the number 99, and let's create another one called c, and let's give that one the value that gets returned from fun1, and then we can print out that value like that. So we've now got our functions. That's all been set up. I can run the program by calling debug. So I either click on the middle button over here on the left. So I've pressed, oh, sorry, that should have been C out. So I press the F5 key, it lets our program run, and we can see that the program runs and it gives us that output. What we want to do though is we want to debug and we want to step through it line by line. So I'm going to add in a breakpoint at this position over here, when I press F5, we'll see that the program launches again, and the program stops at that point. So now this box over here shows us the call stack. We can see at the first level it's got our main function, and we're currently on line 16, and when we click on that we can see that it shows us all the variables inside that frame on the call stack. So in this case we've got A, we've got C, and they both have values 0. So we can take our first step, and so we can say step over, and that will go from A, and we see that that now gives A the value 99. We're now calling a function, and so now we want to step in, and so we can go step into, and we press F11, and so we now see that fun1 has been pushed onto the stack, and fun1 is now on top of the stack. We finished main when we were in line 17, so that one's now waiting at line 17, and fun continues at line 6. We can see inside the fun frame, we can see all our different variables, A, B, and P, and at the moment they all just have garbage values because we haven't given them any values yet. So now we can take a step, and so A equals 4 gets run, and we can see that the variable 4, the value 4 now gets saved into variable A. We can run the next line, so B and 16 get saved into B, and then we can see here, when we take the next step, we can see that P now gets the value 12. When we go to the way that the debugger is showing it at the moment is that it's automatically dereferencing P for us, but it is possible to view the actual address itself. If we take the next step, it should now have printed out all of those values. So we see it printed out 4, 16, and 12. And then from there, it returns B. So now that value got saved into C. So variable C now has the value 16, and we run through and it prints. We can see that when that function returned, we can see that that was popped off of the call stack, and so main is the only function on the call stack. And now as we go through there, our program should finish, and now we see a whole bunch of other extra things. That's just the operating system finishing up our program. So I hope that this gives you a bit of an idea of how to trace functions using the call stack. It's very important to know what kind of variables you're working with. Are those variables allocated on the stack? Are those variables allocated on the heap? When we allocate memory dynamically, so maybe let's put in some notes. So those ones are done on the stack. This one is allocated on the heap. And it's very important to remember that once we allocate something with new, we have to delete it with delete in order to give that memory back to the operating system and avoid a memory leak. Whenever you have to trace functions, particularly if those functions are recursive, so if the functions call themselves, it's very, very useful to be able to write these functions down and to follow exactly what's happening using the stack, because it makes it much, much easier to follow what's going on. So please make sure to read through your notes and read more about the stack and the heap. This kind of allocation is very important in C++, and so it's important that we get used to it before we start looking at more complex data structures.